What if I told you that scientists just captured 32 million galaxies in a single photograph? The Vera Rubin Observatory in Chile has just released its first images, and they're absolutely mind-blowing. We're looking at a view of the Virgo cluster 54 million light-years away, captured by the largest digital camera ever built, a 3.2 gigapixel monster the size of a small car. But here's what will shock you even more. This is just the beginning of something that will revolutionize how we understand our universe. The story begins high in the Chilean Andes, where the Vera Rubin Observatory has finally opened its eyes to the universe. For decades, astronomers have dreamed of building a facility that could not just take still snapshots of the sky, but reveal it in motion, alive and evolving in real time. Now, with the release of its very first image, we are witnessing the dawn of that new era. This first image is nothing short of breathtaking. It captures the southern portion of the Virgo cluster, the closest large gathering of galaxies to our own Milky Way. The Virgo cluster lies around 55 million light-years away, but through Rubin's eyes, it appears as though the cosmos itself has been pulled into sharp focus. Spread across the vast frame are galaxies of every size and shape, shimmering stars that range in color from icy blue to deep crimson, and background smudges that are actually entire clusters of galaxies far beyond Virgo itself. The scale of what Rubin has captured is staggering. In this single image, astronomers can count more than 10 million galaxies. Each of those galaxies contains billions of stars, countless planets, and mysteries we have not yet begun to explore. And yet, this enormous cosmic census was not the result of years of patient exposure. Rubin assembled it in just 7 nights of observing, combining nearly 1,200 individual exposures into one seamless masterpiece. What makes this accomplishment so extraordinary is not only the beauty of the image itself, but the speed and depth with which it was achieved. No other telescope in the world today can capture such a wide field of the universe with this level of clarity in such a short amount of time. It is like taking a panoramic photograph of the cosmos, but at a resolution so high that even the smallest and faintest objects stand out in remarkable detail. Looking closely, you can see nearby spiral galaxies glowing with bluish arms where stars are still forming, while massive elliptical galaxies shine with softer yellow tones, home to older stars whose formation has long since slowed. In the background, clusters of galaxies appear as faint red smears, some of them more than 1 billion light-years away. Rubin does not just reveal a single patch of sky. It unveils layers upon layers of cosmic history, stretching from our local neighborhood out to the deep universe. This single release has already set a new standard for astronomy. For the first time, humanity has the tools to create not only images of astonishing depth, but to begin mapping the dynamic story of the universe itself. The first picture is just a taste of what the next 10 years will bring. At the very core of the Vera Rubin Observatory lies its most remarkable feature, the LSST camera, officially the largest digital camera ever constructed for astronomy. This machine is not just large by the standards of technology. It is literally the size of a small car, standing taller than most people and weighing in at an astonishing 3,000 kilograms. To move it, you would need a heavy-duty crane, not the careful hands of scientists. And yet, for all its size and weight, its purpose is delicate: to capture the faintest whispers of light that have traveled across the universe for millions, even billions of years. The LSST camera carries with it an incredible 3.2 gigapixels. To put that number in perspective, imagine laying out about 1,500 high-definition television screens side by side. Only then would you begin to approximate the sheer detail contained in a single Rubin image. Every shot the camera takes is so sharp and so wide that astronomers can zoom in endlessly, uncovering stars, galaxies, and cosmic structures that were invisible to earlier instruments. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, Give this video a like so we know to keep uncovering them. The heart of the camera is its vast focal plane, made up of 189 highly sensitive charge-coupled device sensors, each one with a resolution of 4,000 by 4,000 pixels. These sensors are not arranged randomly. They are carefully tiled together, forming a perfectly aligned mosaic that covers an area larger than a human handprint. To ensure they can pick up even the faintest glimmer of light, the sensors are cooled to nearly minus 100 degrees Celsius. At such low temperatures, thermal noise, the random static that could drown out weak signals from distant galaxies, is suppressed, allowing Rubin to reveal details no other survey telescope has captured. Complementing this extraordinary camera is the observatory's primary mirror, measuring 8.4 meters, or roughly 28 feet across. This giant mirror is among the largest ever constructed for an optical telescope, giving Rubin immense light-gathering power. But size is only part of the story. What makes Rubin unique is how this mirror and camera work together. The combination produces an extraordinarily wide field of view, spanning 3.5 degrees of sky. That may sound small at first, but in astronomical terms, it is vast. For comparison, the full moon in the night sky covers only about half a degree. Rubin sees 40 times that area in a single exposure, sweeping across the heavens like a cosmic searchlight. This combination of size, sensitivity, and speed allows Rubin to do something no other observatory has achieved. It can survey huge swaths of the universe in record time, capturing both depth and breadth simultaneously. While other telescopes may focus deeply on a narrow slice of the sky, Rubin paints with a far broader brush, giving us not just detailed portraits, but sweeping cosmic panoramas. Every element of this system has been engineered to work seamlessly. The immense camera, the precision sensors, the massive mirror, and the telescope's rapid movement system all come together to form a machine unlike any built before. It is not just a camera. It is a time machine, gathering photons that left their sources long before humans even walked the Earth. With each exposure, Rubin pulls us further back into cosmic history, showing the universe as it was millions or even billions of years ago. And the most exciting part is that the LSST camera has only just begun to reveal its power. If the first images already showcase tens of millions of galaxies, imagine what will emerge when this record-breaking instrument surveys the sky night after night for an entire decade. Most telescopes throughout history have worked like still cameras. They take deep snapshots of the universe, capturing incredible detail in one frame, but only at a single moment in time. The Vera C. Rubin Observatory changes that approach forever. Instead of focusing on static images, Rubin has been designed to scan the entire southern sky once every 3 nights. Over the course of 10 years, this will produce the first ever time-lapse movie of the universe itself. Think about what that means. Imagine watching galaxies evolve, stars brighten and dim, and cosmic explosions unfold not as isolated events, but as part of a living, moving story. By revisiting the same regions of sky again and again, Rubin allows astronomers to witness change on a cosmic scale. Events that were once hidden, fleeting, or easy to miss will now appear in sharp detail, captured almost in real time. Among the most exciting targets are supernovae, the violent deaths of massive stars. These explosions can briefly outshine an entire galaxy, but they happen unpredictably, and they fade quickly. With Rubin's constant sweeping of the sky, astronomers won't miss them. The telescope will detect a supernova at the moment it ignites, allowing scientists to study the full evolution of the blast as it expands, cools, and leaves behind a neutron star or a black hole. Rubin will also track variable stars, whose brightness shifts due to pulsations, eclipses, or changes in their outer layers. Studying these variations helps astronomers measure distances across the universe and probe the internal structures of stars themselves. With a decade of high-resolution monitoring, Rubin will produce the most detailed catalog of stellar variability ever assembled. But the time-lapse sky survey doesn't stop with stars. Rubin will monitor black hole flares, the brief outbursts of energy released when matter spirals into these cosmic giants. For decades, these events were often spotted only by chance. Now, scientists will see them systematically, gaining insight into how black holes grow and interact with their surroundings. Closer to home, Rubin's moving picture of the heavens will revolutionize our understanding of the solar system. The telescope is expected to discover millions of asteroids, including potentially hazardous ones that cross Earth's orbit. By tracking their movement night after night, astronomers can refine their orbits and assess whether any of them pose a real danger. For planetary defense, this alone makes Rubin one of the most important scientific projects of our time. The beauty of Rubin's approach lies in its combination of speed and persistence. Other observatories may catch glimpses of these phenomena, but Rubin will record their entire stories. For the first time, humanity will watch the universe in motion, seeing the cosmos not as a static backdrop, but as a dynamic, evolving stage. What we will gain from this decade-long cosmic movie is almost impossible to predict fully. Surprises are certain. New classes of objects, unexplained bursts of energy, or even signs of phenomena that challenge our physics could all emerge. Rubin is not just about confirming what we already know, it is about opening the door to what we do not yet understand. One of Rubin's most powerful tools is something known as difference imaging, a technique that turns ordinary photographs into a discovery engine. The concept sounds simple at first, but in practice, it represents one of the most sophisticated data processing methods ever used in astronomy. Here's how it works. Rubin begins by creating what astronomers call template images. These are reference portraits of every region of the southern sky, assembled under the best possible observing conditions. The templates capture the background universe in incredible detail, the stars, galaxies, and clusters that remain steady and unchanging. Think of them as a cosmic baseline. Then, as Rubin scans the sky night after night, it produces fresh images of the same regions. Each new frame is carefully aligned with the template and compared pixel by pixel. Anything that remains the same, fixed stars, distant galaxies, the steady glow of background light, is digitally subtracted away. What remains in the difference image are the changes, the surprises, the events that tell us the universe is alive. This subtraction process highlights new stars that suddenly appear in the night sky, variable stars whose brightness has shifted since the template was made, asteroids that have inched their way across the frame, or distant supernovae that weren't there before. By stripping away the static background, Rubin transforms the overwhelming flood of celestial data into a manageable set of the most important signals. The scale of this process is staggering. Every single night, Rubin will reveal around 10 million changing or moving objects. That means that by the time the telescope has completed its first week of surveying, it will have cataloged more new events than most observatories discover in years of work. Each of these detections will be analyzed, flagged, and distributed to astronomers across the globe in near real time, allowing the scientific community to react instantly to new discoveries. Imagine the power of this. A star in our galaxy begins to flare, and within minutes, researchers on the other side of the world receive an alert. A potentially hazardous asteroid drifts across the sky, and its orbit is refined before breakfast. A distant supernova ignites, and telescopes around the planet swing into position to capture its earliest moments. Rubin doesn't just take pictures, it creates a living, breathing monitoring system for the universe. The difference imaging technique also ensures that nothing is overlooked. Human eyes alone could never sift through the billions of stars and galaxies Rubin observes, but the algorithms can. They detect the faintest flickers of change, far below what we might otherwise notice, and they do it with mechanical precision. In this way, Rubin becomes more than a telescope. It is a guardian of the sky, watching for every shift, every flicker, every new light in the darkness. This approach will redefine how astronomers work. Instead of hunting blindly for rare events, they can let Rubin's system deliver them directly. It transforms astronomy from a field of chance discoveries into one of systematic, nightly revelations. And the sheer number of events Rubin will capture means that we are bound to stumble upon phenomena we never even imagined. With difference imaging, Rubin brings us a universe that is not static, but ever-changing, a cosmic landscape alive with motion, transformation, and surprise. The Vera C. Rubin Observatory is not only powerful, it is astonishingly fast. Every 30 seconds, its massive LSST camera captures a 3.2 gigapixel image of the sky. To grasp how much data that is, imagine trying to take a single photograph so detailed that you could zoom in on a grain of sand from miles away. Now imagine doing that every half a minute, all night long. What makes this feat even more remarkable is the speed at which the observatory handles this torrent of information. Each colossal image, containing more than 3 billion pixels, is read out and stored in just 2 seconds. By the time most telescopes would still be processing a single exposure, Rubin is already preparing for the next one. But the speed isn't only in the data. It's built into the telescope itself. The observatory's structure weighs an incredible 600 tons, yet it is engineered with such precision that it can pivot from one patch of the sky to another in only 5 seconds. Picture the scale of this movement. Hundreds of tons of steel and glass swinging smoothly into perfect alignment with the stars, again and again, dozens of times per hour, without missing a beat. This agility makes Rubin unlike any large telescope before it. It is a giant, but one that moves with the grace of a dancer. The combination of these capabilities is what allows Rubin to cover the entire visible southern sky in just 3 nights. No other facility has ever come close to achieving such breadth with such depth. Other telescopes might spend weeks or months mapping even a fraction of the same territory. Rubin can sweep across it in a matter of days, and then return to do it all over again, night after night, year after year. For a full decade, this relentless cycle creates a rhythm, a cosmic heartbeat of observation. Every 3 nights, Rubin refreshes our picture of the universe, ensuring that nothing goes unnoticed. A new supernova explosion? Rubin will catch it. An asteroid shifting its orbit? Rubin will track it. A distant galaxy flaring to life? Rubin will record the change before we even realize it is happening. It's not just about speed for speed's sake, though. The precision with which Rubin operates ensures that these rapid-fire observations are scientifically invaluable. Each exposure is perfectly aligned, calibrated, and compared to the last, building a data set of extraordinary consistency. This level of reliability is essential because even the tiniest variations in brightness or position can signal major astrophysical events, whether it's the wobble of a star caused by an unseen planet or the subtle dimming of light as an asteroid passes in front of a distant galaxy. By uniting unprecedented speed with meticulous precision, Rubin gives astronomers the best of both worlds, the ability to monitor the cosmos in real time while maintaining the accuracy needed for groundbreaking science. For the first time in history, we will not just take snapshots of the universe. We will track its unfolding drama, step by step, frame by frame. This capacity for rapid, precise, wide-field observation is what transforms Rubin from a powerful telescope into a revolutionary one. It doesn't just expand our vision of the universe, it accelerates it, bringing us discoveries at a pace humanity has never experienced before. When Rubin's first images were unveiled, they weren't just beautiful, they were packed with scientific treasures. Each frame revealed layers of the universe, from the nearest objects in our Milky Way to galaxies billions of light-years away, all captured with breathtaking clarity. Among the highlights is Messier 49, or M49, a massive elliptical galaxy located within the Virgo cluster. Unlike spiral galaxies with their graceful arms, ellipticals like M49 are ancient and rounded, glowing with the soft, reddish light of old stars. Its population has long since stopped forming new suns, leaving behind a dense city of aging stars that tell the story of an earlier cosmic epoch. Through Rubin's sharp gaze, The subtle colors of these stars stand out, giving astronomers a detailed map of one of the oldest galactic giants in our cosmic neighborhood. Nearby in the same image lies a striking contrast, Messier 61, or M61, a face-on spiral galaxy alive with activity. Brilliant blue regions reveal pockets where new stars are being born in vast clouds of gas and dust. At its center lurks a supermassive black hole, a monster millions of times the mass of our Sun. With Rubin's sensitivity, astronomers can trace the star-forming regions across M61's spiral arms and study the interaction between the galaxy's vibrant core and its outer disk. Together, M49 and M61 embody two extremes of galactic evolution: the quiet, ancient elliptical, and the lively, star-forming spiral. But Rubin's first images didn't stop there. Perhaps the most dramatic sight of all was a triple galaxy merger, a rare cosmic ballet where three massive galaxies are colliding and slowly coalescing into one. Their distorted shapes, twisted arms, and tidal streams of stars reveal the violent process of galactic evolution, a process that our own Milky Way will undergo billions of years from now when it merges with the neighboring Andromeda galaxy. Rubin captured this merger with such clarity that astronomers can follow the faint arcs of starlight stretching out into intergalactic space, a reminder that the universe is constantly reshaping itself. Looking deeper, the image unveils reddish galaxy clusters scattered across the background. These clusters lie billions of light-years away, their light traveling to us since before the Earth even formed. Each faint red smear is not a single galaxy, but hundreds or thousands bound together by gravity, surrounded by vast halos of dark matter. By cataloging such clusters across the sky, Rubin will help map the large-scale structure of the universe and trace how it has grown under the mysterious influence of dark energy. Closer to home, Rubin's wide-field view reveals brilliant foreground stars within our own Milky Way. Their intense light is diffracted through the camera's optics, producing striking cross-shaped spikes that stretch across the image. Though purely instrumental artifacts, these spikes add to the visual drama of the scene, reminding us that even the nearest stars shine with overwhelming power when seen through Rubin's massive lens. And then there are the unexpected visitors, thin, glowing streaks cutting across the frame. These are asteroid trails, left as small rocky bodies drift through our solar system during the long exposures. To most telescopes, such trails are nuisances, obscuring background objects. But for Rubin, they are valuable data points. Each streak is a trackable object, a marker of the countless small bodies orbiting the Sun. By catching thousands of these trails night after night, Rubin will build the most complete census of asteroids ever attempted. Altogether, these first images demonstrate exactly what Rubin was built to do: capture the universe in all its scales and dimensions, from the local and familiar to the remote and mysterious. Every layer, galaxies, clusters, stars, and asteroids, comes together in a single breathtaking field of view, a preview of the billions of discoveries yet to come. While Rubin's first images immediately dazzled with distant galaxies, one of its most practical and groundbreaking achievements lies much closer to home: the discovery of asteroids within our own solar system. These small rocky bodies, often no larger than a house, zip silently through space, sometimes crossing the orbit of Earth. Tracking them is not just an academic exercise, it's essential for planetary defense. In a mere 10 hours of observation, Rubin identified 2,100 new asteroids, a staggering number when you consider that all other ground-based and space observatories combined typically find around 20,000 asteroids in an entire year. This rapid-fire discovery is a testament to Rubin's unprecedented combination of speed, precision, and wide-field coverage. Every night, the telescope sweeps across vast sections of the sky, capturing fleeting streaks of light that indicate these fast-moving objects. Even if they are small, faint, or distant, these asteroid discoveries are more than just numbers. Each new object adds to our understanding of the population of small bodies in the solar system. Their sizes, orbits, and compositions reveal the history of our planetary neighborhood, telling the story of collisions, migrations, and the gradual formation of planets billions of years ago. Some of these asteroids have never been observed before, providing entirely new insights into the building blocks of our solar system. Perhaps most importantly, Rubin's survey dramatically improves our ability to detect near-Earth objects, asteroids whose orbits bring them close to our planet. By cataloging millions of these bodies over its 10-year mission, Rubin will help astronomers identify any that could pose a future threat. This makes the observatory not just a window to the distant universe, but a powerful early warning system, safeguarding humanity from potential cosmic hazards. The scope of Rubin's asteroid discoveries is unprecedented. It is expected to catalog up to 5 million asteroids over the course of its survey, increasing the known population fivefold. This enormous database will allow scientists to study patterns in asteroid orbits, compositions, and interactions on a scale never before possible. For the first time, we will have a near-complete map of the solar system's small bodies, from the inner asteroid belt between Mars and Jupiter to the far reaches of the Kuiper belt beyond Neptune. And the implications don't stop at numbers. With precise tracking of their movement, Rubin can help identify clusters of asteroids influenced by unseen gravitational forces, refine models of solar system dynamics, and even contribute to the search for the hypothesized Planet 9. Every asteroid trail captured, every faint streak of light recorded, is a new piece of a cosmic puzzle that spans billions of years and billions of kilometers. In this way, Rubin's asteroid discoveries bridge the gap between deep space exploration and practical, immediate science. While it peers billions of light-years into the universe, it simultaneously protects our tiny planet and expands our understanding of the celestial neighborhood we call home. While Rubin's images stretch billions of light-years into the distant universe, they also capture the breathtaking processes occurring much closer to home. Among the highlights of its first data releases are two iconic stellar nurseries, the Lagoon Nebula and the Trifid Nebula, both located within our Milky Way galaxy. These regions are cosmic cradles where new stars are born, and Rubin's unprecedented resolution brings them into extraordinary focus. The Lagoon Nebula, roughly 4,000 light-years away, glows with a vivid pink hue, revealing clouds of gas collapsing under their own gravity to form clusters of young stars. These newborn stars are far from passive. Their intense radiation and stellar winds sculpt the surrounding gas, carving intricate shapes and clearing cavities within the nebula. Rubin's images capture these dynamic interactions in exquisite detail, allowing astronomers to trace how individual stars influence their environment and how clusters of stars come together to form larger systems. Above the Lagoon Nebula lies the Trifid Nebula, another stellar nursery located about 5,000 light-years away. The Trifid is remarkable for its combination of structures: a pink emission nebula, a blue reflection nebula, and dark dust lanes dividing it into 3 distinctive lobes, hence its name. Rubin's sharp imagery allows us to see newborn stars embedded within these clouds, their light illuminating and sculpting the surrounding gas and dust. The nebula becomes a laboratory for studying the earliest stages of star formation, showing how gravity, radiation, and turbulence interact to create new suns. Through Rubin's lens, these nebulae are not static objects frozen in time. They are living, evolving regions, full of motion and transformation. By comparing images taken over multiple nights and months, astronomers will be able to observe changes in brightness, movement of gas and dust, and the emergence of new stars. This dynamic perspective provides insights into processes that were previously invisible, revealing how massive clouds collapse, how clusters of stars emerge, and how young stars begin shaping their cosmic cradles. Understanding these stellar nurseries is essential because they provide the blueprint for how galaxies, Star clusters and planetary systems form and evolve. Each bright knot of light in the Lagoon or Trifid Nebula is a potential solar system in the making, a glimpse into the very beginnings of stars like our own Sun, and, possibly, worlds like Earth. Rubin's ability to capture these regions in high resolution and track their changes over time offers a level of detail that was previously the domain of a handful of smaller, narrow-field telescopes, but now across a vast portion of the sky. By combining wide-field imaging with incredible depth, Rubin bridges the gap between nearby stellar nurseries and the distant galaxies it surveys. In doing so, it gives astronomers a complete view of the life cycles of stars, from their birth in nebulae to their explosive deaths in supernovae and beyond. Each image is a chapter in the ongoing story of the universe, showing us not only where stars come from, but how they continue to shape the cosmos around them. The Vera C. Rubin Observatory is not just a technological marvel. It is a tool designed to tackle some of the biggest unanswered questions in astronomy and physics. Its mission spans 4 major scientific frontiers, each offering transformative potential for our understanding of the cosmos. The first frontier is the transient sky. Many cosmic events are fleeting. Supernovae, gamma-ray bursts, and fast radio bursts can appear suddenly and vanish in a matter of days, hours, or even seconds. Rubin's rapid, repeated surveys of the southern sky make it uniquely suited to catch these transient phenomena. The observatory is expected to detect around 100,000 supernovae each year, spanning from relatively nearby explosions to events occurring billions of light-years away. By observing these explosions almost immediately after they ignite, astronomers can study the physical processes behind stellar deaths in unprecedented detail and refine key measurements such as cosmic distances using supernovae as standard candles. The second frontier involves dark matter and dark energy, the invisible forces that govern the structure and fate of the universe. Together, these mysterious components make up roughly 95% of the cosmos, yet remain largely undetected. Rubin will map their distribution using a technique called weak gravitational lensing, which measures the subtle distortions of light from distant galaxies as it passes through intervening matter. By analyzing these distortions across billions of galaxies, astronomers can create a 3-dimensional map of dark matter, track how structures form and evolve, and probe the accelerating expansion of the universe driven by dark energy. These observations could help answer fundamental questions about the very nature of reality itself. The third frontier is a comprehensive census of the solar system. Rubin will catalog millions of asteroids, including near-Earth objects, providing a far more complete inventory than ever before. It will also extend its reach to smaller, icy objects in the Kuiper Belt, a distant region of the solar system beyond Neptune. Some of these objects may even provide indirect evidence for the hypothesized Planet 9, a massive, as yet unseen planet, whose gravitational influence appears to shape the orbits of certain distant bodies. By surveying these populations in detail, Rubin not only advances planetary science, but also contributes to the safety of our planet by identifying potential impact threats. The fourth and final frontier is Milky Way archaeology. By surveying billions of stars, including faint stars in the galaxy's outer halo, Rubin will help reconstruct the Milky Way's history. One key focus is stellar streams, long, faint trails of stars left behind when smaller galaxies were torn apart by the Milky Way's gravity. These streams act as fossil records, preserving clues about ancient galactic mergers and the formation of our galaxy over billions of years. With Rubin, astronomers will piece together the Milky Way's dynamic evolution star by star, creating a detailed history of how our cosmic home came to be. Taken together, these 4 scientific frontiers show the breadth and ambition of Rubin's mission. It is not just a telescope, it is a comprehensive survey instrument that will simultaneously explore the transient, the invisible, the nearby, and the distant. In doing so, Rubin promises to reshape our understanding of everything from the smallest asteroids in our solar system to the largest structures in the universe and the fundamental forces that govern them. The Vera C. Rubin Observatory carries a name that is synonymous with one of the most groundbreaking discoveries in modern astronomy. Vera Rubin, the pioneering astronomer for whom the observatory is named, transformed our understanding of the cosmos in the 1970s. Through meticulous measurements of galaxy rotation curves, Rubin revealed that stars in galaxies were moving far too fast to be held together by visible matter alone. This provided the first compelling evidence for the existence of dark matter, an invisible substance that dominates the mass of the universe but cannot be seen directly. Her work not only revolutionized astrophysics, but also opened an entirely new field of inquiry into the unseen forces shaping galaxies and cosmic structures. Rubin's legacy goes far beyond the discovery itself. She demonstrated the power of careful observation, rigorous data analysis, and relentless curiosity in uncovering the hidden truths of the universe. Today, the observatory that bears her name carries forward that spirit of exploration on a scale she could only have imagined. By scanning the entire southern sky every few nights for a decade, Rubin will collect data that addresses some of the biggest open questions in astronomy: the nature of dark matter and dark energy, the formation and evolution of galaxies, the dynamics of stellar populations, and the transient events that light up the universe. The observatory is uniquely positioned to transform our cosmic understanding. Its unprecedented combination of speed, depth, and breadth allows it to map the invisible structures of the universe, track millions of asteroids in our solar system, and catch fleeting phenomena that have remained hidden until now. Just as Vera Rubin's careful measurements of a few dozen galaxies challenge the established understanding of matter, this new generation of observations promises to challenge and expand our knowledge of the universe on a truly massive scale. By connecting the discoveries of the past with the technologies of the future, the Vera C. Rubin Observatory ensures that Rubin's influence continues to guide astronomy. It honors her commitment to observation and her insistence on following the data wherever it leads. Over the next decade, this observatory will likely uncover phenomena that we cannot yet even imagine, shedding light on the universe's most profound mysteries and inspiring a new generation of astronomers, physicists, and curious minds around the world. In essence, the Vera C. Rubin Observatory is not just a tribute, it is a living continuation of her work. It embodies the idea that curiosity, combined with vision and technology, can reveal the unseen, transform our understanding of reality, and expand humanity's place in the cosmos. As the telescope begins its 10-year survey, it carries forward Rubin's legacy, exploring the invisible, mapping the dynamic sky, and pushing the boundaries of what we know about the universe. The Vera C. Rubin Observatory marks the beginning of a new era in astronomy. From the first breathtaking images of distant galaxies to the discovery of thousands of asteroids in our own solar system, Rubin is already reshaping how we see the universe. Over the next decade, it will provide an unprecedented, dynamic view of the cosmos, capturing not just snapshots, but the ever-changing motion of stars, galaxies, and cosmic phenomena. It is more than a telescope. It is a time machine, a cosmic camera, and a guardian of our solar system, all in one. By revealing the invisible structures of dark matter, tracking the influence of dark energy, mapping our galactic neighborhood, and observing the fleeting moments of stellar explosions, Rubin will answer questions humanity has long pondered, while undoubtedly uncovering mysteries we have yet to imagine. And it all begins with curiosity, the same spirit that guided Vera Rubin to discover the unseen mass shaping galaxies. Her legacy lives on in every exposure, every pixel, and every discovery this observatory will produce. The universe is alive, dynamic, and full of surprises, and Rubin gives us the tools to watch it unfold in real time. So, as we look up at the night sky, from the stars in our own Milky Way to galaxies billions of light years away, we can do so with new eyes and endless possibilities. The Vera C. Rubin Observatory is not just observing the cosmos, it is connecting us to it, inspiring generations of scientists, and reminding us that there is always more to discover. The story of the universe is still being written, and with Rubin, we are finally turning the pages in real time. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.